More than 1 million miles from Earth, a machine now drifts. It is quietly redefining our universe. For decades, scientists believed the cosmos was unimaginably vast yet measurable, spanning about 14 billion light-years. Then, the James Webb Space Telescope aimed its mirrors into what seemed like empty darkness. That long-held confidence began to break. Webb revealed galaxies forming far earlier than expected. It showed black holes growing faster than theory explains, and structures appearing when the universe should still have been in its infancy. Yet, the most unsettling discovery isn't just how far Webb sees. It's what these findings suggest about reality's true scale, and how much of the universe may forever remain beyond our reach. To grasp what the James Webb Space Telescope truly reveals, we first need to adjust a simple, but deeply misleading, idea about the universe. We tend to think space is something we merely look across, like a landscape stretching into the distance. In reality, the universe does not behave like that. In the cosmos, distance is not just distance. It is also time. Light travels at a constant speed, roughly 300,000 kilometers per second. It is the fastest thing that exists, fast enough to circle the entire Earth more than 7 times in a single second. At human scales, that speed feels instantaneous. Our senses treat light as if it arrives the moment it leaves its source. But across the enormous distances of the universe, even light cannot eliminate delay. The moment light leaves an object, its journey begins. When you glance across a room, you are seeing the past by a few billionths of a second. This delay is so small the brain ignores it entirely. When you look at a distant building, the delay stretches slightly longer, into millionths of a second. Even then, it remains too small to matter in everyday life. However, the universe operates on scales far beyond our daily experience. When you look at the moon, the light reaching your eyes left its surface about 2 seconds earlier. The moon you see in the sky isn't the moon as it is right now, but as it was 2 seconds in the past. When you look at the sun, that delay grows to roughly 8 minutes. Sunlight must cross 150 million kilometers before reaching Earth. If the sun were to suddenly vanish at this instant, the sky would not go dark immediately. For 8 more minutes, sunlight would continue arriving, carrying information from a star that no longer existed. From there, the delays quickly become enormous. The nearest star beyond our sun appears to us as it was more than 4 years ago. When astronomers observed the center of the Milky Way, the light entering their instruments began traveling toward us roughly 26,000 years in the past. Long before the earliest human civilizations emerged. And when telescopes observed the Andromeda galaxy, the light we detect today left its stars about 2 million years ago. Long before recorded history, even before modern humans spread across the planet. The night sky, in other words, is not a live view of the universe. It is a historical record. Every star, every galaxy, every faint point of light carries a timestamp from the moment its light began crossing the cosmos. Each photon arriving at Earth today has been traveling through space for years, centuries, or even billions of years. The farther away an object is, the older the story its light tells. But the universe does not preserve these messages unchanged. Space itself is expanding. This idea may sound abstract, but it profoundly impacts how we observe the cosmos. Galaxies are not simply moving away from one another through empty space. Instead, the fabric of space itself is stretching, gradually increasing the distances between galaxies over time. And when space stretches, the light traveling through it stretches as well. As light crosses billions of light-years of expanding space, its wavelength gradually lengthens. Energetic blue light shifts toward red, and eventually slips into infrared wavelengths, which are invisible to the human eye. Astronomers call this effect redshift. Redshift is more than a color change, it acts as a cosmic timestamp. The more the light is stretched, the longer it has been traveling, and the earlier in the universe's history it must have been emitted. Distance and time become inseparable. Looking farther into space means looking deeper into the past. For decades, astronomers relied on telescopes designed mainly to observe visible light. This is the narrow range of wavelengths our eyes evolved to detect. Instruments such as the Hubble Space Telescope revolutionized astronomy, revealing stunning details of galaxies, star-forming clouds, and nebulae scattered across the nearby universe. But as scientists tried to push their observations further back, toward the beginning of cosmic history, the universe began to appear strangely empty. Not because it was truly empty, but because its light had changed. As light from the earliest galaxies traveled across the expanding universe, its wavelength stretched beyond the visible spectrum. By the time that light finally reached Earth, much of it had shifted into infrared wavelengths that earlier telescopes were not optimized to detect. To those instruments, large portions of the early universe seemed dark. But the darkness was deceptive. It was not emptiness, it was simply light that had moved beyond our ability to see it. The James Webb Space Telescope was designed specifically to detect that hidden light. Instead of focusing on visible wavelengths, Webb is built to observe infrared radiation. This allows it to capture signals from galaxies whose light traveled over 13 billion years. Its mirror spans more than 6 meters across and is coated with a thin layer of gold, chosen for its excellent infrared reflectivity. This design allows Webb to gather incredibly faint signals that earlier telescopes could not detect. But detecting infrared light presents a major challenge. Infrared radiation is closely connected to heat. Any warm object emits infrared light, including telescopes themselves. If Webb were warm, it would glow in the same wavelengths it is trying to observe, drowning out the delicate signals arriving from distant galaxies. To avoid this, Webb must remain extremely cold. A giant, 5-layer sun shield, roughly the size of a tennis court, blocks heat and light from the Sun, Earth, and Moon. On the shadowed side of that shield, the telescope cools to temperatures around -230 degrees Celsius. At those temperatures, Webb becomes quiet enough to detect ancient light's faintest whispers. The telescope operates nearly 1.5 million kilometers from Earth, at a stable gravitational balance point known as Lagrange 2. From this distant location, shielded from heat and interference, Webb can stare into deep space for long periods without interruption. When Webb turns its mirrors toward a region of sky that appears completely black to our eyes, it is not searching for nothing. It is waiting. Waiting for photons that began their journey when the universe was still young. Those photons do not arrive quickly. Sometimes they reach the telescope one by one, carrying faint signals from galaxies whose light has been traveling across billions of years of cosmic history. Webb may observe the same patch of sky for hours or even days, patiently collecting these ancient photons until a picture slowly begins to emerge. And what appears in that darkness is not silence. Galaxies begin to reveal themselves where emptiness once seemed to exist. Systems already forming stars, already building structure, already evolving in ways that challenge earlier expectations. The early universe does not look fragile or incomplete. It looks active. Each image Webb produces is not a simple snapshot. It is a mosaic assembled from ancient light, with every photon in the frame having traveled across billions of years before reaching the telescope. By the time that light arrives, the stars that produced it may already be gone, and the galaxies that emitted it may have changed dramatically. What we see is not the universe as it is today. It is the universe as it once was. For this reason, astronomers often describe telescopes like Webb not simply as tools for looking far away, but as instruments for looking backward through time. Nearby galaxies reveal the universe closer to the present day. More distant galaxies show earlier stages of cosmic history. And the most distant objects ever detected reveal the universe when it was still very young. But even the extraordinary reach of the James Webb Space Telescope has a limit. There is a boundary beyond which no telescope can see. Not because of technological limitations, but because of the fundamental physics of the universe itself. Light has had only a finite amount of time to travel since the beginning of the cosmos, which means there is a maximum distance from which light could possibly have reached us. Astronomers call this limit the observable universe. It is not the edge of space. It is the edge of information. Beyond that boundary, the universe continues to exist. Galaxies form and evolve. Stars ignite and collapse, and black holes merge in regions whose light will never reach Earth. Simply because space's expansion prevents those signals from ever crossing the immense distance. The James Webb Space Telescope has not revealed the edge of everything that exists. Instead, it has revealed how much of reality lies beyond what we can ever observe. And as Webb pushes closer to that boundary, detecting galaxies earlier and earlier in cosmic history, a deeper realization begins to emerge. If the universe appears this rich and structured at the very limits of our vision, then the true scale of everything beyond that horizon must be far greater than we once imagined. For many years, astronomers believed they had a reasonable picture of how the early universe unfolded. The Big Bang filled space with hot, dense matter, which then expanded and cooled. Gravity began working quietly in the background, slowly gathering material together. Over time, small irregularities in that nearly uniform matter distribution grew stronger, pulling gas inward and forming the first stars and galaxies. In this picture, cosmic evolution was expected to be gradual. The earliest galaxies should have been small and faint. They were envisioned as fragile collections of stars just beginning to take shape. Gas needed time to cool and collapse. Dark matter halos needed time to grow large enough to trap ordinary matter. And the formation of stars themselves required millions of years. Even after the first stars appeared, assembling large galaxies was thought to be a slow process, involving repeated mergers and steady accumulation of material. The early universe, according to these expectations, should have been relatively quiet. Not empty, but sparse. When the James Webb Space Telescope began observing extremely distant regions of space, astronomers expected to find only a handful of primitive galaxies, scattered through a young cosmos that was still building its first structures. Instead, Webb found crowds. Bright galaxies appeared again and again in eras that should have contained very few of them. These were not dim sparks barely holding themselves together. Many were already forming stars at remarkable rates, producing enormous amounts of light. The surprise was not a single unusual object. It was the pattern. Again and again, Webb detected galaxies during the universe's first few 100 million years that were far brighter and more massive than theoretical models had predicted. Some of these systems already contained hundreds of millions, or even billions, of solar masses worth of stars. According to long-standing models of galaxy formation, building structures of that size should have taken much longer. Gravity is powerful, but it is not instantaneous. Gas clouds do not collapse the moment gravity begins pulling on them. They must first lose energy and cool before they can contract efficiently. Dark matter halos must grow large enough to trap ordinary matter. Stars must form, evolve, and enrich their surroundings with heavier elements before galaxies can develop complex structures. Each step requires time. And yet, when Webb looked into the early universe, many of those steps seemed to have already happened. Even more intriguing was the chemical composition of some of these young galaxies. Webb detected elements such as carbon and oxygen within them. These elements were not created during the Big Bang. They are produced inside stars, and stars release them into space only when they die, often in spectacular supernova explosions. Their presence in early galaxies suggests that at least one generation of stars had already formed, lived their lives, and ended in explosive deaths before the galaxies we now observe even came into existence. The cosmic timeline appeared to be compressing. Events that scientists believed required hundreds of millions of years may have happened much faster. To appreciate why this puzzled astronomers, it helps to imagine building a city. You cannot construct skyscrapers before roads exist. And you cannot pour concrete before producing steel. Each stage depends on the one before it. The early universe was expected to be laying foundations. Instead, Webb seemed to find buildings already rising. This growing mismatch between theoretical expectations and observation became known informally among researchers as the problem of too much light too early. When astronomers estimated how much light galaxies should produce during the universe's first billion years, their calculations consistently predicted far less brightness than Webb was detecting. The difference was not small. In some cases, the observed galaxies appeared several times brighter than predicted. When confronted with such a discrepancy, scientists naturally look first for simpler explanations. Perhaps the measurements were misleading. Perhaps dust inside these galaxies was affecting the observations, or gravitational lensing from intervening galaxies was magnifying distant systems, making them appear brighter than they truly were. Another possibility involved the presence of rapidly feeding black holes at the centers of these galaxies. As matter spirals into a black hole, it can release tremendous amounts of energy, producing intense light that might make a galaxy appear larger or more luminous than it actually is. These possibilities were investigated carefully. In some cases, actively feeding black holes did contribute additional brightness. Accounting for their influence helped reduce some of the most extreme mass estimates for early galaxies. But the broader pattern remained. Even after corrections were applied, the early universe still appeared to contain significantly more bright galaxies than standard models predicted. The tension eased somewhat, but it did not disappear. Webb repeated these observations in different parts of the sky, using multiple instruments and wavelengths, and the results remained consistent. The early universe appeared surprisingly active, with star formation occurring at an unexpectedly rapid pace. This forced astronomers to reconsider a key assumption: how efficiently the universe can convert gas into stars. In the modern universe, star formation is surprisingly inefficient. Most gas inside galaxies never becomes stars. It is heated by radiation, stirred by turbulence, or blown away by stellar winds and supernova explosions. Only a small fraction eventually collapses into new stars. The early universe may have behaved very differently. One possibility is that conditions were simply denser. In the universe's youth, galaxies were closer together, and gas clouds were packed more tightly than they are today. Frequent collisions between galaxies may have compressed gas and triggered bursts of rapid star formation. Another possibility involves the composition of the earliest gas clouds. The first stars formed from almost pure hydrogen and helium, without heavier elements that influence how gas cools and collapses. These simpler conditions may have allowed star formation to proceed in ways that modern galaxies no longer experience. Mergers likely played an important role as well. When galaxies collide, gas is driven inward toward their centers, becoming compressed and heated. This process can ignite intense waves of star formation, producing large numbers of stars in a relatively short period of time. Each of these explanations may account for part of the puzzle, but none of them fully resolves it. Adding to the mystery, Webb has also detected evidence for supermassive black holes existing far earlier in cosmic history than expected. Some of these black holes appear to have formed when the universe was less than 500 million years old. Yet, they already contain millions or even billions of times the mass of the Sun. According to conventional models, black holes begin as the collapsed remnants of massive stars, typically containing only a few tens of solar masses. Growing them into supermassive objects should require long periods of steady feeding and repeated mergers. Yet Webb continues to detect massive black holes at astonishingly early times. This has pushed astronomers to consider possibilities that once seemed unlikely. Perhaps the earlier stars were far more massive than modern stars, collapsing directly into large black holes. Perhaps enormous clouds of gas collapsed directly into black holes without forming stars first. Or perhaps the early universe contained conditions that allowed black holes to grow far more rapidly than we currently understand. For now, none of these explanations has been confirmed, but none can be dismissed either. What makes these discoveries especially important is that the earliest galaxies shaped everything that followed. Their radiation altered the state of the universe's gas. Their supernova explosions spread heavy elements across space. And their gravity helped build the large-scale structures that would eventually evolve into galaxy clusters and cosmic filaments. If galaxies formed earlier and faster than expected, then the entire timeline of cosmic evolution may need to be reconsidered. The universe may have assembled its first major structures far more quickly than scientists once believed. And as the James Webb Space Telescope continues to peer deeper into space and further back in time, the same pattern keeps emerging. The early universe was not hesitant. It was already in motion. Stars were forming, galaxies were growing, and black holes were already gathering mass. All within a cosmic era that was once expected to be nearly empty. The universe did not wait. It began building itself almost immediately. For much of modern astronomy, scientists believed they had arrived at a surprisingly solid answer to one of the largest questions imaginable: how many galaxies exist in the universe? The method seemed straightforward, even if the scale was extraordinary. Astronomers would point a powerful telescope at a very small patch of sky that appeared almost completely empty. They would then count every galaxy visible in that tiny region and use that number to estimate how many similar regions exist across the entire sky. If you know how many galaxies occupy a small sample of the universe, you can scale that number up to approximate the whole. When the Hubble Space Telescope carried out one of the deepest observations ever attempted, the results stunned even the scientists involved. In a tiny patch of sky no larger than a grain of sand held at arm's length, Hubble revealed nearly 10,000 galaxies. The image became famous as the Hubble Ultra Deep Field. Before that observation, many astronomers suspected that distant space might become increasingly empty as telescopes looked further outward. Instead, Hubble showed the opposite. The deeper it looked, the more galaxies appeared. From those observations, astronomers estimated that the observable universe contained roughly 100 to 200 billion galaxies. The number was almost impossible to comprehend. Yet for many years it remained the best estimate available. Then the James Webb Space Telescope began looking at the same darkness. Where earlier images showed scattered islands of light separated by black space, Webb revealed additional layers of structure. Regions that once appeared empty began to glow faintly in infrared wavelengths. Galaxies that had been invisible to previous instruments slowly emerged from the background. This was not because earlier telescopes had made mistakes. It was because they were looking in the wrong part of the spectrum. As light from distant galaxies travels across billions of years of cosmic expansion, its wavelengths stretch. Light that originally shone in visible wavelengths gradually shifts into infrared. By the time it finally reaches Earth, much of it has moved beyond the range that older telescopes were designed to detect. The galaxies were always there. Their light had simply drifted beyond the limits of our vision. The James Webb Space Telescope was built specifically to follow that stretched light. Its instruments are designed to detect infrared radiation with extraordinary sensitivity, allowing it to reveal galaxies that earlier telescopes could not see. When Webb began conducting its deep field observations, it once again pointed toward regions of sky that appeared nearly empty. But instead of seeing a handful of distant objects, Webb uncovered dense layers of galaxies stacked across cosmic time. In some deep observations, hundreds of thousands of galaxies appeared within a relatively small portion of the sky. Each of those galaxies contains enormous numbers of stars. Some contain billions, others contain trillions. Many host clouds of gas and dust where new stars are still forming, and many likely contain planetary systems orbiting those stars. The universe, it turns out, is not sparsely populated with isolated galaxies drifting through empty space. It is crowded. What makes this realization even more remarkable is that Webb does not simply detect galaxies. It can measure them. By analyzing the redshift of their light, astronomers can estimate how far away each galaxy is, and therefore how far back in time it formed. Webb can also estimate the rate at which those galaxies are forming stars and the approximate amount of mass they contain. When scientists combine all of these measurements, they can begin to reconstruct the history of galaxy formation across billions of years. And when that history is assembled, a striking pattern emerges. Galaxies are not scattered randomly across space. They gather together. On the largest scales, galaxies form vast interconnected structures stretching across hundreds of millions of light-years. These structures resemble enormous filaments, linking galaxy clusters together in long strands that span unimaginable distances. Between these filaments lie enormous voids, regions of space containing very few galaxies at all. Taken together, the pattern resembles a gigantic three-dimensional web. Astronomers call this structure the cosmic web. This pattern is not accidental. It emerged gradually from the earliest moments of cosmic history. After the Big Bang, matter was distributed almost evenly throughout space. But tiny fluctuations in density were present from the very beginning. Regions that were slightly denser exerted slightly stronger gravitational pull. Over time, matter slowly flowed toward those regions, amplifying the differences. Gravity drew material inward, forming dense filaments and clusters, while leaving behind vast regions where very little matter remained. A helpful way to imagine this process is to picture rainfall across a landscape. Water flows downhill, collecting in valleys and carving rivers through the terrain. Over time, a structured network of channels forms, while higher ground remains relatively dry. In a similar way, matter flowed through the universe under the influence of gravity, gradually forming the vast filaments and clusters that define the cosmic web. The James Webb Space Telescope is helping astronomers map this structure with far greater clarity than ever before. Because it can detect extremely distant galaxies that were previously invisible, Webb fills in missing pieces of the cosmic map. Entire populations of faint galaxies have now appeared where earlier surveys saw only darkness. It contains information about how the universe evolved. The way galaxies cluster together reveals how matter moved through space over billions of years, how gravity shaped large-scale structures, and how the earliest fluctuations in matter eventually grew into the vast cosmic architecture we observe today. Webb's observations show that many of these structures began forming surprisingly early. Some long filaments of galaxies already existed when the universe was only a few billion years old. In some regions, galaxies appear tightly grouped together, suggesting that gravity was already sculpting large clusters earlier than many models had predicted. But the cosmic web is not just a network of galaxies. It is also defined by emptiness. Between its dense filaments lie enormous cosmic voids, regions where almost no galaxies exist. Some of these voids span tens or even hundreds of millions of light-years. If an observer were located near the center of one, they might look out in every direction and see almost nothing at all. These voids are among the largest structures in the universe by volume. The universe, in other words, is both crowded and empty at the same time. Dense clusters of galaxies sit along immense filaments, while vast regions of near darkness stretch between them. And when astronomers use Webb's deep field observations to estimate the total number of galaxies that might exist across the observable universe, the numbers become staggering. The earlier estimate of 100 billion galaxies now appears to be only part of the picture. If Webb's observations are representative of the wider universe, the true number could be far larger, possibly trillions of galaxies. Each containing stars, each containing planets, each representing an entire island of cosmic history unfolding across billions of years. Yet, even this enormous number refers only to the portion of the universe we can observe. Beyond the limits of our vision, space continues. Galaxies continue. The cosmic web extends into regions whose light will never reach us. And if the universe already appears this rich within the boundaries we can see, the true scale of everything beyond them becomes almost impossible to imagine. At first glance, the size of the universe seems like it should be straightforward to estimate. The Big Bang occurred about 13.8 billion years ago. And since light travels at a constant speed, it feels natural to assume that the most distant objects we can observe should lie about 13.8 billion light-years away. In everyday terms, that reasoning seems perfectly logical. Yet, the real picture is far more surprising. In reality, the observable universe has a radius of about 46 billion light-years, giving it a total diameter of roughly 93 billion light-years. This number is not speculation or exaggeration. It follows directly from measurements of cosmic expansion and from the behavior of ancient light traveling through space. What makes this result feel so counterintuitive is that it conflicts with the way we instinctively think about movement and distance. Nothing can move through space faster than the speed of light. And that rule still holds across the entire universe. No galaxy is racing through space at impossible speeds. And no signal is breaking the fundamental limit set by physics. The confusion arises because the expansion of the universe does not involve objects flying through space the way fragments fly outward from an explosion. Instead, something far stranger is happening. The universe expands by stretching space itself. When astronomers say that distant galaxies are moving away from us, the statement can easily create the impression that galaxies are traveling outward through empty space like ships leaving a harbor. But on the larger scales, galaxies are not really traveling through space in that way. Rather, the space between galaxies is gradually expanding, increasing the distance that separates them. A helpful analogy is to imagine small dots drawn across the surface of a balloon. As the balloon inflates, each dot moves farther away from every other dot. Not because the dots themselves are sliding across the surface, but because the surface itself is stretching. Every dot sees the others drifting away, even though none of them sits at a special center. The large-scale expansion of the universe behaves in much the same way. When a distant galaxy emitted the light that our telescopes detect today, it was far closer to our region of space than it is now. During the billions of years that light traveled toward Earth, the universe continued expanding, steadily stretching the distance between galaxies. By the time the light finally arrived here, the galaxy that emitted it had already been carried tens of billions of light-years farther away. This is why we can observe galaxies whose light has been traveling for more than 13 billion years. Even though the galaxies themselves now lie much farther away than 13 billion light-years, the light we observe has not crossed a fixed distance. Instead, it has traveled through space that was continuously expanding during the journey. In effect, the path the light had to cross kept growing as the light moved along it. Early in the universe's history, the expansion rate was slower, which allowed light to make steady progress across space. Over billions of years, however, the expansion of the universe accelerated, stretching distances faster and faster. Some photons began their journeys early enough to eventually reach us despite that expansion, while others never will. This situation naturally creates a boundary, but it is not a wall and it is not an edge in the ordinary sense. Astronomers refer to it as the cosmic horizon, a limit that marks the farthest distance from which light has had enough time to reach us since the beginning of the universe. Beyond that horizon, space continues to exist. But the light from those regions has simply not had enough time to arrive here. The important point is that the cosmic horizon does not represent the edge of the universe itself. It represents only the edge of what we are able to observe from our particular location in space and time. Several lines of evidence strongly suggest that the universe continues far beyond that boundary. When astronomers examine the distribution of galaxies across the sky, they do not see the density of galaxies fading toward an edge. Instead, the universe appears broadly similar in every direction. The faint afterglow of the Big Bang, known as the cosmic microwave background, also appears remarkably uniform across the sky, a pattern that would be extremely unlikely if space abruptly ended just beyond our visible region. All of this points to a simple but unsettling conclusion. The universe almost certainly extends far beyond the portion we can observe. Beyond the cosmic horizon, there may be galaxies, clusters, and enormous cosmic structures similar to the ones we see nearby. Yet, the light from those regions will never reach us because the space between us and them is expanding too quickly. No matter how powerful our telescopes become, they cannot overcome that fundamental limitation. Even more intriguingly, the cosmic horizon itself is not fixed. As time passes, the observable universe slowly grows larger because light from increasingly distant regions has had more time to travel toward us. In that sense, the horizon gradually expands outward. At the same time, however, cosmic expansion is accelerating, meaning that the distances between galaxies are stretching faster than they were in the past. These two processes operate together in complex ways. Some galaxies that were once invisible eventually become observable as their light finally reaches us, revealing new regions of the universe that were previously hidden. At the same time, other galaxies are gradually carried so far away by cosmic expansion that the light they emit today will never reach Earth. Over extremely long periods of time, those galaxies will effectively disappear from view. If the expansion of the universe continues at its current rate, future observers tens of billions of years from now may see a dramatically different sky. Nearly every galaxy outside our own local group will have drifted beyond the cosmic horizon, leaving only a small cluster of nearby galaxies visible in an otherwise dark universe. From their perspective, it might appear as though the universe contains only a handful of galaxies. They might never realize that the cosmos was once filled with trillions. This idea also changes how we think about observation itself. The observable universe is not a universal boundary that applies everywhere. It depends entirely on where the observer happens to be located. An observer in a distant galaxy billions of light-years away would see a different observable universe than we do, with some regions of space visible to them that remain forever hidden from us. Every location in space effectively sits at the center of its own observable universe. There is no single viewpoint from which the entire cosmos can be seen. This is why telescopes like the James Webb Space Telescope are so important. By detecting galaxies closer to the cosmic horizon than any instrument before it, Webb pushes our window of observation as far as physics allows, revealing structures that formed when the universe was still in its early stages. Yet even Webb cannot see beyond the horizon. The galaxies whose light it detects from the edge of the observable universe are not where they appear in the images we capture. Their light began traveling billions of years ago, and during that immense journey, the universe has continued expanding. The galaxies themselves may have changed dramatically since the moment that light was emitted. What we observe is therefore not the present universe, but a collection of ancient signals arriving from distant moments in cosmic history. And beyond the boundary from which those signals originate lies a far larger universe that remains permanently hidden from view. The James Webb Space Telescope has not discovered an edge to the cosmos. Instead, it has revealed something far more profound. The universe may extend far beyond the limits of what any observer can ever see. For most of the 20th century, the story of the universe seemed relatively clear. The Big Bang set everything in motion. Space began expanding, and gravity slowly worked to shape the cosmos. Galaxies gathered into clusters. Stars formed inside swirling clouds of gas, and the large-scale structure of the universe gradually emerged. Underlying that picture was a simple assumption. Gravity, the force that pulls matter together, was expected to slow the expansion of the universe over time. Since every galaxy contains enormous amounts of mass, and mass attracts other mass, astronomers assumed that the outward motion left over from the Big Bang must gradually be losing momentum. The galaxies flying apart should have been slowing down as gravity tugged them back toward one another. For decades, the central question in cosmology was not whether expansion was slowing, but how quickly. Some scientists even wondered whether gravity might eventually halt the expansion entirely and reverse it, causing the universe to collapse back in on itself in a distant future, sometimes described as the Big Crunch. Then, near the end of the 1990s, astronomers made a discovery that changed that picture completely. Two independent teams of researchers were studying distant stellar explosions known as Type 1a supernovae. These events occur when certain types of stars reach a critical mass and explode with extraordinary brightness. Because these explosions reach nearly the same peak luminosity each time they occur, astronomers can use them as reliable cosmic mile markers. By comparing how bright a supernova appears in the sky with how bright it is known to be, scientists can estimate how far away it is. When that distance is compared with how quickly the host galaxy is moving away from Earth, astronomers gain insight into how the expansion of the universe has changed over time. The results were deeply unexpected. The expansion of the universe was not slowing down. It was accelerating. Distant galaxies were farther away than they should have been if gravity alone were shaping the expansion. The deeper astronomers looked into space, the clearer the pattern became. Instead of gradually losing speed, the expansion of the universe had been increasing for billions of years. Something was pushing space apart. To account for this mysterious effect, cosmologists introduced a new concept called dark energy. Dark energy cannot be observed directly. It does not shine, absorb light, or emit radiation that telescopes can detect. Instead, its existence is inferred from its influence on the expansion of the universe. Yet, despite being invisible, dark energy appears to dominate the cosmos. Current measurements suggest that roughly 68% of the universe consists of dark energy. Ordinary matter, the atoms that make up stars, planets, gas clouds, and living things, accounts for less than 5% of the total cosmic inventory. Most of the remaining mass exists as dark matter, another invisible component whose nature remains one of the great mysteries of modern physics. In other words, the familiar universe of stars and galaxies represents only a tiny fraction of reality. What makes dark energy especially strange is how it behaves as the universe expands. Normal matter becomes diluted as space grows larger. If the volume of the universe increases, the same amount of matter spreads out across a greater distance, reducing its overall density. Radiation behaves similarly, thinning even faster as the universe stretches. Dark energy does not follow that pattern. Instead, the density of dark energy appears to remain nearly constant even as space expands. As the universe grows larger, more dark energy effectively fills the additional volume. The total amount of it increases along with the expansion itself. This creates a remarkable feedback effect. The more the universe expands, the more dark energy exists, and the greater the influence it has on cosmic expansion. Over billions of years, this process gradually shifted the balance of power in the universe. In the early cosmos, matter dominated. Gravity shaped the formation of galaxies and clusters, pulling gas inward and building the cosmic web of structure that telescopes now observe. But as space expanded and matter became increasingly diluted, dark energy began to play a larger role. About 5 billion years ago, dark energy became the dominant influence on cosmic expansion. From that point onward, the expansion of the universe began accelerating. The James Webb Space Telescope does not observe dark energy directly, but its influence appears everywhere in the data Webb collects. The enormous size of the observable universe, the extreme stretching of ancient light, and the way distant galaxies recede into the depths of space all reflect the effects of accelerated expansion. Without dark energy, the universe we observe today would look very different. The cosmic horizon would lie much closer to us because expansion would have slowed more dramatically over time. Many of the distant galaxies that Webb now detects would never have reached the positions we observe today. In a sense, dark energy has stretched the universe open. It has allowed the observable cosmos to grow to the immense scale we see today. But dark energy does more than shape the present universe. It also determines its long-term future. If dark energy continues behaving as current observations suggest, then cosmic expansion will continue accelerating indefinitely. Gravity will still hold galaxies and clusters together on local scales, but on the larger scales, the distances between cosmic structures will keep increasing. Over immense stretches of time, more and more galaxies will drift beyond the cosmic horizon. Trillions of years from now, observers living inside a galaxy like the Milky Way may look into the sky and see only their own galaxy and a few nearby companions. The rest of the universe will have expanded so far away that its light can no longer reach them. In that distant era, the cosmos may appear almost empty, which makes our own moment in cosmic history somewhat unusual. We exist at a time when the universe is old enough for galaxies to have formed across enormous distances, yet young enough that we can still observe many of them. Even so, the story of cosmic expansion contains a puzzle that scientists are still trying to resolve. When astronomers measure how fast the universe is expanding today, two different methods produce slightly different answers. One method examines the very early universe by studying the cosmic microwave background. This is the faint radiation left over from when the universe was only about 380,000 years old. Patterns within that ancient light allow scientists to calculate an expansion rate of roughly 67 kilometers per second for every megaparsec of distance. A second approach focuses on the nearby universe. Astronomers measure distances to galaxies using Cepheid variable stars and Type I supernovae, then compare those distances with the observed speeds at which galaxies are moving away from us. This method consistently produces a higher expansion rate, around 73 km per second per megaparsec. Both techniques rely on extremely precise observations and have been tested repeatedly using independent data. Even after years of careful scrutiny, however, the two results still do not match. This disagreement is known as the Hubble tension. It represents one of the most intriguing mysteries in modern cosmology. If both measurements are correct, then our current understanding of how the universe expands may be incomplete. The James Webb Space Telescope was expected to help clarify the situation by improving the accuracy of distance measurements in the nearby universe. Instead, Webb's observations have strengthened the evidence for the higher expansion rate. Rather than resolving the discrepancy, the new data has made the tension more difficult to ignore. This leaves cosmologists facing several possibilities. There may be subtle errors hidden within one of the measurement techniques, or there may be new physics influencing the expansion of the universe in ways that scientists have not yet fully understood. Whatever the explanation turns out to be, the discovery of dark energy has already transformed our understanding of the cosmos. It revealed that the universe is not simply expanding, it is accelerating. Dark energy stretches space itself, steadily pushing distant galaxies farther apart and shaping the cosmic horizon that limits what we can observe. Yet, dark energy is only one half of the invisible forces that govern the universe. Because while dark energy drives expansion on the larger scales, something else must pull matter together on smaller scales, allowing galaxies, clusters, and the vast structures seen by the James Webb Space Telescope to form. That unseen influence is known as dark matter, and it provides the hidden framework that holds the universe together. If dark energy determines how the universe expands, another invisible component determines how it holds together. Without this second ingredient, the universe revealed by modern telescopes would not exist in anything like its present form. Galaxies would struggle to form. Clusters would disperse, and the large-scale pattern stretching across the cosmos would never have emerged. This hidden component is known as dark matter. Dark matter does not emit light, reflect light, or absorb radiation in any way that telescopes can detect. In that sense, it is completely invisible. Yet, its gravitational influence is unmistakable, and the amount of it present in the universe appears to be enormous. Current measurements suggest that about 85% of all matter in the universe is dark matter. Everything familiar, stars, planets, clouds of gas, dust, and even the atoms in our own bodies, makes up only a small fraction of the total mass. What we see is only the illuminated surface of a much larger structure. The first hints that something unseen was influencing galaxies appeared nearly a century ago. Astronomers studying the rotation of spiral galaxies noticed that stars in the outer regions were orbiting far faster than expected. According to the laws of gravity, those stars should have been flung outward into intergalactic space if only visible matter were holding the galaxies together. But they were not escaping. Instead, the outer stars continued circling their galaxies at high speeds as if they were embedded within enormous halos of unseen mass. The visible stars and gas were only a small part of the total gravitational structure. Something invisible was providing additional gravity. As observations improved over the decades, similar evidence began appearing on larger scales. Entire galaxy clusters contained far more gravitational pull than could be explained by the matter astronomers could see. When scientists examined how galaxies moved within those clusters, the motion suggested that vast quantities of hidden mass were present. Another powerful line of evidence came from a phenomenon known as gravitational lensing. According to Einstein's theory of general relativity, massive objects bend the path of light passing near them. When astronomers observed distant galaxies through large clusters of foreground galaxies, they saw the background light being distorted and magnified. By measuring those distortions, scientists could estimate how much mass was present in the cluster. Again and again, the calculations showed that visible matter alone was not enough. The majority of the mass was invisible dark matter. Although it cannot be seen directly, its behavior appears to be relatively simple. Unlike ordinary matter, which collides, heats up, and emits radiation, dark matter seems to interact mainly through gravity. It moves through space without friction and does not lose energy the way normal gas does. This difference had enormous consequences during the early history of the universe. Shortly after the Big Bang, matter was spread almost evenly across space with tiny variations in density scattered throughout the young cosmos. Dark matter responded to those variations first. Because it did not interact with radiation, it was free to begin clumping together under the pull of gravity, while ordinary matter remained too hot and energetic to collapse. Over time, these clumps grew into massive halos of dark matter. Invisible structures hundreds of thousands of light-years across began forming long before the first stars ever ignited. As the universe cooled, ordinary matter gradually fell into these dark matter wells. Gas collected within them, became compressed, and eventually heated enough to ignite nuclear fusion. The first stars were born. Those stars later gathered into galaxies. But the locations where galaxies formed were not random. They formed precisely where dark matter had already created the deepest gravitational wells. In this way, the visible universe followed a hidden blueprint. Dark matter shaped the landscape, and ordinary matter illuminated it. This process produced one of the most remarkable patterns in nature, the cosmic web. On the largest scales, galaxies are arranged along enormous filaments that stretch across tens and hundreds of millions of light-years. These filaments intersect at dense nodes where galaxy clusters form, while vast empty regions known as cosmic voids occupy the spaces between them. The result resembles a three-dimensional network woven across the entire observable universe. For many years, this cosmic web existed mainly in computer simulations. Cosmologists used powerful supercomputers to model how dark matter should behave over billions of years, and the results consistently produced a filament-like structure strikingly similar to what astronomers observed. The James Webb Space Telescope is now helping confirm these predictions with unprecedented detail. By detecting hundreds of thousands of galaxies and measuring their distances, Webb allows astronomers to map how galaxies are distributed across vast regions of space. These maps show galaxies tracing long strands across the universe, gathering into clusters at intersections, and leaving behind enormous voids where very few galaxies exist. In other words, the cosmic web is not just a theoretical idea. It is an observed structure. Even more remarkable is the way matter appears to flow along these filaments. Gas and smaller galaxies move gradually along these cosmic pathways, feeding larger galaxies and clusters over time. Galaxies are not isolated islands drifting randomly through space. They are connected parts of a much larger gravitational network. Our own galaxy participates in this structure. The Milky Way is part of a group of galaxies embedded within a larger filament of the cosmic web. Over immense timescales, gravity continues to guide the motion of galaxies along these pathways, slowly reshaping the large-scale structure of the universe. Yet, despite decades of research, the true nature of dark matter remains unknown. Scientists have proposed many possible explanations. Some theories suggest that dark matter consists of undiscovered particles that interact only weakly with ordinary matter. Others explore the possibility that it could involve entirely new forms of physics beyond the current understanding of particle theory. Experiments around the world are searching for signs of dark matter particles, while telescopes continue examining its gravitational effects across the cosmos. So far, however, the particles themselves have never been detected directly. Despite that uncertainty, the presence of dark matter is nearly impossible to deny. Remove it from our models of the universe, and the cosmic structures we observe cannot be explained. Galaxies would not remain stable, clusters would disperse, and the vast web of matter stretching across the universe would never have formed. Dark matter provides the scaffolding on which the visible universe is built. At the same time, dark energy continues stretching space on the larger scales, slowly pushing distant galaxies farther apart. The universe, therefore, exists in a delicate balance between two invisible influences. One that builds structure through gravity, and another that drives expansion across cosmic distances. Together, these forces shape everything we observe. The stars, galaxies, and glowing clouds captured by telescopes like Webb are only the visible layer of a much deeper reality. Beneath that shining surface lies an unseen architecture guiding the formation of structure across billions of years. And even that vast interconnected universe represents only the portion we can observe from our small position in space and time. Beyond the cosmic horizon, the universe almost certainly continues, filled with galaxies, stars, and structures shaped by the same invisible forces. The James Webb Space Telescope has not shown us the edge of the universe. Instead, it has revealed something far more profound. The deeper we look into the cosmos, the clearer it becomes that what we can see may be only a small glimpse of a much larger reality. A reality containing an astounding, incomprehensible number of galaxies, many, many, many trillions.